Hi, my name is Daniel Hickox-Young. I'm from St. Olaf College, and I'm going to be talking about the normal modes of a mass spring chain system. In particular, those associated with a non-uniform array of spring constants. Let's begin by taking a look at some of the mathematics required to model a mass spring chain. If we consider a generic series of n springs and n masses, we can describe the motion of the system with a set of equations of the following form. These second-order linear differential equations can be solved with the relation shown here, where q represents the amplitude of oscillation. If all the springs and masses are identical, we can solve for the eigenfrequencies and their associated amplitudes fairly easily from here. But since we're interested in a more general solution, we will continue. If we solve for q sub j plus 1, we end up with a recursive definition for the amplitudes, which we can then rewrite in matrix form. As it turns out, this equation may be more easily analyzed with a change of basis. So we define a new variable, p, and substitute, producing a much more convenient transfer matrix. From here, we can solve for q sub j plus 1 once again, and we're just about ready to model some systems. Now all we need to do is use a computer engine to solve numerically for the eigenfrequencies using the boundary conditions, namely that the end masses or the walls are fixed, and then plug each of these frequencies into our equation for q to find the amplitudes of each mass at a given eigenfrequency. Now before proceeding on to some simulations, I'd like to acknowledge Amy Kolan, Barry Cipra, and Bill Titus, who's demonstrated this method of calculating normal modes in their paper on localization in non-periodic systems. For the first simulation, I've used identical masses and identical springs as a point of reference for when we begin to look at more interesting systems. Note that while the masses are displayed as oscillating in the vertical direction, this is just a tool to make the oscillations easier to visualize. In reality, the motion we are mapping is in the horizontal direction. As we examine this lowest mode, recall that the standing wave pattern seen here can be thought of as the result of constructive and deconstructive interference between traveling waves as they reflect off the walls in perfect resonance. We observe the same thing in this second mode, only the so-called traveling waves have half the wavelength of those in the first mode. This same principle can be applied to the second highest and highest modes. Note that for all these modes we observe a very symmetrical standing wave, stretched across all the unfixed masses, such that with the exception of a few nodes in the intermediate eigenfrequencies, energy is transferred to all the masses in the system. Now this is pretty cool, but let's take a look at what happens when we replace one of the springs with one that's 4 times as stiff. Here's the second highest mode again. Look at how the oscillations are restricted to masses on the right side of the stiffer spring. We see a standing wave pattern similar to the one before, but the wave doesn't travel down the full length of the chain. Instead, the stiff spring acts as a wall, reflecting the wave back down the right side of the chain, leaving the masses on the left side of the spring more or less unaffected. If we look at the highest mode, we see that the oscillation is almost entirely restricted to the masses on either side of the stiff spring. This concentration of energy in a few masses is called localization. If we look at a plot of the mode number versus frequency for these two systems, we notice something interesting. For the uniform array of spring constants, the eigenfrequencies increase at a gradually decreasing rate relative to the mode number. For the case with one stiffer spring, we see the same pattern except the final frequency is significantly higher than the others, because it takes more energy to drive the stiffer spring. We see a particularly interesting relationship between mode number and frequency if we use an array of spring constants that alternate between stiffer and looser springs. Note the two branches on this plot. The upper one is referred to as the optical band, while the lower is called the acoustical band, separated by a distinct band gap. This plot is exciting to look at, but what does this mean physically? Looking at the fourth mode, solidly in the acoustical band, we see that the masses on either side of the stiff springs are coupled together, hardly moving at all, so that all the energy of the system is being transferred to the loose springs. The same is true here at the 10th mode, but what happens if we look at the 11th mode, the first member of the optical band? Here we first start to see oscillations in the stiffer springs, and continue to see more for the higher modes of this system. Similarly to what we saw before, the stiffer springs only oscillate significantly when there's enough energy in the system, and this is a significantly higher energy level than for the looser springs, thus causing the gap between frequencies for the optical and acoustical bands. Now, perhaps the coolest thing we can look at is what happens when we use a random distribution of spring constants. Pictured here is the highest mode for a mass spring chain with a random distribution of spring constants. Remarkably, the oscillation appears to be localized, similarly to the case of a single stiff spring in an array of looser springs. If we look at the next mode, we again observe localization, almost to the same degree that was observed in the highest mode. In fact, we observe restriction of the oscillations to one part of the chain all the way down to the 15th mode, shown here. If we check the specific spring constants that appear on either side of the localization, we observe that the border or division between the oscillating masses and the non-oscillating masses is often marked by either a spring that's somewhat looser than those around it or a spring that's somewhat stiffer. In the case of the stiffer spring, incoming waves reflect off the spring as off a wall, traveling back down the chain, interacting constructively and deconstructively, forming the standing wave pattern. In the case of the looser spring, incoming waves again reflect, but this time the spring produces the same result as an unfixed end, causing the wave to travel back down the same side of the chain it was first traveling on. If we check a plot of frequency versus mode number, we get more clues as to what's going on. Although gaps aren't nearly as dramatic as those for the system with alternating spring constants, we still observe a highly irregular distance between eigenfrequencies. Since the spring constants are randomly distributed, the energies required to drive them are randomly distributed as well. So after all this analysis and the simulations, you may be well asking yourself, so what? Why do we care about the normal modes of a mass spring chain system? Well, as it turns out, there's a number of applications. A mass spring chain is directly analogous to a series of inductors and capacitors, which can be used as a model in electronics. The optical and acoustical bands observed with the case of the alternating spring constants are again directly analogous to the conduction and valence bands used in material science. And perhaps most interestingly, the localization of energy associated with the random distribution of spring constants can be directly related to the change in properties of material which has been disordered by the addition of a foreign material, thus changing the distribution of effective spring constants or bonds between adjacent atoms. So in conclusion, varying the spring constants of a mass spring chain produces many interesting results which can be directly applied to other fields. Thank you very much for watching, and special thanks to Professor Amy Kolan for her help on this project.